Everyone, my name is Tarik Bellamine, and I'm a systems engineer. I'm joined by my teammates, Joshua Reback, an electrical engineer, Kevin Burke, a mechanical engineer, and Amy Wu and Jonathan Bryan, both material science engineers. What we've designed is an add-on to a standard desktop 3D printer that allows the everyday user to produce fully functioning electromechanical objects through the integration of plastic materials, conductive materials, and separately fabricated components. Now, to give you guys an understanding of what we've done, first we're going to give you a background on what 3D printing is, what our solution is, how you use it, how it works, and some of its future implications. So, everybody is familiar with the concept of 2D printing. You have a file on your computer, you type some words, throw in a table, maybe a few pictures, and out comes a physical copy of what you designed. Imagine a world where 3D printing was just as easy. All you'd have to do is design any conceivable device on your computer, press print, and out would come your printed product ready to use. So what we've done was, so the way 3D printing works is through a method called fused deposition modeling. What this means is that plastic material is heated up and pushed out of a fine nozzle. Layer upon layer of material is stacked upon one another until you're left with your finished 3D object. So the problem is that 3D printers are capable of printing only static plastic objects. This limitation is what motivated our project. We wanted to add on this capability to produce fully functioning electromechanical devices. Our starting point was this MakerBot Replicator 2X, one of the most popular 3D printers on the market today. So what we've done is augmented this MakerBot to have the capability to print electromechanical devices. What this means is that not only can our MakerBot print plastic material, but it can also lay down highly conductive traces and integrate separately fabricated components, such as motors, batteries, and even control boards, all in a live automated print and behind a very friendly user interface. So the goal of our project was to make a product that was low cost, minimally invasive, highly automated, can print highly conductive materials, and be very precise. So now that we have an understanding of what our solution is, next we're going to talk about how the user interacts with our augmented 3DPI MakerBot.
Okay, so how do you go from a design in your head to a functional electromechanical product using what we're going to call our 3DPI printer right here? So we've designed it so that the process is fairly straightforward in comparison to using the existing MakerBot Replicator 2X. So the first step is to design what you want to print. I'll just give you a brief overview of the steps. The first step is designing what you want to print. The next step is preparing your design for electromechanical printing, because as we said, normal MakerBots can only print in plastic. We need to enable the functionalities to extrude conductor and picking and placing prefabricated parts. The next step is simply loading this updated file onto an SD card, pop it in the printer, and you're ready to go. So as you can see, the only additional step here is this simple preparation step, where you run your design through our print integration script. So let's go through each of the steps in more detail. So the first step is to design what you want to print using some type of computer-aided design software, such as SolidWorks. Now, if you're printing an electromechanical device, you need to design two things. One is the plastic shell, and two is the conductive traces. So as you can see, the next step is importing these designs into Makerware, which is MakerBot's proprietary software. So you can see the gray is the plastic shell of Quadrotor, which is the electromechanical device we're going to use as our example. And these traces here, these thin gray traces which are about to turn red, are the conductive traces. So in this step, we're simply merging the designs in Makerware and queuing it up for 3D printing. So right now, we have a file that corresponds to a plastic print. And Makerware will make you what's called a G-code file of that plastic print. So G-code is a low-level programming language. It essentially provides the lowest layer of control over what the MakerBot actually does. So G-code allows you to do things like control where and how quickly to move the extruders, even toggling individual outputs on the MakerBot circuit board. So G-code is predictably hard to read and hard to write. So we've architected our system so the user doesn't have to do either one. Instead, you simply run this G-code file through our print integration script, and the script will parse through the file and add in the appropriate G-code commands to both print conductive traces and pick-and-place motors. And when the user runs the script, they'll see this dialog box to simply enter the coordinates of all the devices, all the prefabricated parts they want to insert into the print. And we'll go into the details of how this works in a bit, but this is the general outline. And as we said, next step is loading it onto an SD card, pop it in the printer, and you're ready to go. So the 3D PI printer will take care of the rest of the process for you. It will do the plastic printing, it will extrude the conductive traces on top, and then it will pick and place the prefabricated parts, in this case a motor, right into that little well we've designed for it. And it moves over, lowers an arm, drops the motor right into place. So, now you know how to use it. How does it all work? To get the full effect of how it works, we kind of need to decompose our product into its component parts. And the component parts are control and integration, a software package, the pick and place functionality, and the extrusion of conductive material. So we've augmented our MakerBot to control and communicate with the various appendages that we've added onto it. And it's this communication and control that really lies at the heart of how this system works. So, to enable this communication, we've hooked into an unused digital output on the MakerBot circuit board. Most people use this extra output for controlling an extra fan, but we're using it for digital signaling. So this signal feeds into an M2 microcontroller, shown here and mounted on top right there, which processes the signal and then powers the appropriate appendage as necessary. So we need to control 5 different functions. That is, there's 5 things that our MakerBot can do that a normal MakerBot replicator has no notion of. Those 5 things are extruding conductive material, lowering and raising a mechanical arm, those kind of 2 separate things, and then opening and closing a clamp. So how do we use one signal to control 5 different things? Now this diagram in the middle, the signal diagram, shows you how our communication protocol works. The first pulse is what we call a control signal. And the length of the control signal determines which of the 5 functions we want to enable. After the microcontroller receives the control signal, it then waits for another high pulse, shown there as T2, and it will power the appropriate motor in the appropriate direction as long as that signal is high.
So now that we've talked about how we communicate with our MakerBot to our system, let's talk about how we generate those signals in the first place. So, as mentioned before, in order to integrate our added functionality into a print, we need to modify our G-code file. So what that means is we send it through the print integration script we've talked about, add a little user input, and out comes our modified G-code file. So because we need to print both plastic and a conductive material, we need to make use of MakerWare's the Replicator 2X's dual extrusion support. So what this means is that the plastic is modeled and extruded as normal, while the conductor is modeled as the second type of plastic that the Replicator 2X can extrude. So once you add that into MakerWare and slice it into the G-code file for the print, our script will slice through that G-code, or will parse through that G-code file. Now when it identifies the command to change to the second extruder, which is this green up here, our code will intercept that command and instead insert our signaling command first in the red here, followed by our execution signal for extruding conductor. Now similar insertions are also made when we reach the layer within the G-code that the user has specified where they'd like to place a component. So next let's talk about the hardware that we've added to our system. So in order to add these separate components into our print, we designed an arm and clamp style end effector. Now these are mounted right onto the extruder head carriage of the MakerBot. This allows us to leverage the precision of the MakerBot's positioning system and also allows us to integrate it into the print more easily as we're allowed to use the existing G-code commands. So that allows the clamp to move within the XY direction as we're able to use the G-code commands to move the extruder head. The arm itself allows the clamp to lower down to the mounting bins to pick up our component and then lower it again into its specified place. So now I'll turn it over to Jonathan to talk about the conductor extrusion.
Thanks, Kevin. So currently, Desktop 3D printers can only print in plastic, which is an insulator. In order to print conductive traces, we have to select a new material based on these 4 main criteria. First and foremost is conductivity. We needed a material that was with low enough resistance to be able to power a small hobbyist motor. Next was adhesion. We needed a material that could stick to the plastic that the MakerBot already prints. And next, viscosity. We needed a material with low enough viscosity that could be controlled in a precise manner. And then finally, cost. We needed something that was affordable to the average hobbyist. So guided by these constraints, we tested numerous materials throughout the year and ultimately selected a colloidal silver seen here, which is composed of 60% silver microparticles suspended in 40% solvent. When the traces are laid down, the solvent evaporates, which leaves behind a highly conductive silver trace. So as you can see, the colloidal silver is a liquid at room temperature, which means that we can't utilize the extruder heads of the MakerBot. Instead, we had to create a new system and integrate it within the hardware of the MakerBot in order to print these silver traces. Ultimately, we decided to go with a syringe-based extrusion mechanism for 2 main reasons. First, the fine needle tips allow for precise and controlled traces. And second, the syringe cartridge closely resembles the storage conditions of the silver, which allows for minimum maintenance by the user. So once we created and fine-tuned this system, our results were great. We were able to print the conductive traces required for a quad rotor in 3 minutes. They dry in 3 minutes, and the silver cost $3. So we prepared a demo. So here's the motor, which was placed into this hole. There's the silver traces were placed here, and this is just to show the conductivity. Jesus.
So on our screen right now, this is showing our live print, which will be extruding conductor within the wells we printed. Right, these are inside. Okay. A little trouble with the leads, but we can come back to that.
Okay.
Yeah, we'll come back to that.
As they're getting our other live demo set up, I'd like to bring everything together. So our aim for this project was to take 3D printing to the next level. Before our product, you may remember that 3D printers could only print limited plastic geometries with very limited functionality. So we were able to build the first ever prototype. Can you go back a slide? The first ever prototype of an affordable 3D printer that can integrate conductors and prefabricated components into one plastic print. So you may recall that we had a set of design objectives that we set out to complete, and we were able to successfully meet all of them. The first was that we wanted the cost of the product to be affordable, under $4,000, so that the average hobbyist could afford it. And we were able to create a product that was only $143 on top of a $2,500 MakerBot system. The second was that we wanted to create a non-invasive design for our solution, and was able to do that by integrating our product with the existing MakerBot hardware. The third is that we wanted to allow the user to be able to do a seamless automated print, and was able to do that by creating a user-friendly software with minimal user input. The fourth was resistivity. So we needed our traces to be low enough resistivity, and we were able to achieve that by discovering a conductive material that was 1.5 times 10 to the negative 6 ohm meters, or conductive enough to power a hobbyist motor. The last two have to do with precision. So we needed our conductive traces to be precise, and we were able to achieve that by printing traces of 0.5 millimeters. And then the last one was the precision of the pick and place, which we were able to do by pick and placing separately fabricated components within 1 millimeter of the designated location. So our project is only the first step into a much larger future of manufacturing. This 3D PI solution makes it possible for hobbyists to print simple electromechanical devices at home. But even looking into the near-term future, with more precision, people could print circuitry at the comfort of their own home, with the long-term vision that people could print 3D electronics at home as well. Now imagine all the possibilities of this integrated technology. Not only could a toy manufacturer such as Hasbro design and rapidly prototype an electronic toy car in-house, but a hobbyist could design and print a control board. A doctor could potentially design and print medical prosthetics that use electronics, such as the hand shown here. And then even within our own Detkin lab, a student could potentially design and print their own circuit boards and test them in the span of one class period. So basically, we're imagining a future where the consumer becomes a producer, where it's as easy as 2D printing. You design a file on a computer, you hit print, and then our solution does the rest. At this time, this concludes our presentation. We'd like to thank many different people for their help and support along the way, including our lovely advisor, Dr. DeHon. Thank you. Are there any questions?